Okay, guys, so we already had one graphing lab, okay, and that graphing lab had to do with position versus time graphs, where obviously we can calculate things like the total displacement of an object, okay, the average speed of an object, okay, using the slope, right, and things like that. So now we're going to look at doing some of the stuff that we've done with graphing, but now with velocity versus time graphs. Okay, so it's not a terribly difficult thing. We'll be building it on Google Sheets, same as we did last time, so we don't have to do anything by hand, and that'll save us a bunch of time, and of course it'll be a lot neater that way too. Okay, so the problem we're investigating here, okay, the change in velocity of a vehicle measured over time tells us acceleration. How can graphing help us calculate acceleration? Okay, that's the problem we're investigating. Now we are hopefully pretty familiar with how exactly we would calculate acceleration from a velocity versus time graph, as that is probably something that's going to be needed in your hypothesis. Okay, variables. Weird thing about this experiment. There's no procedure. I'm just giving you the data. I went online and researched the acceleration times of various cars and found them for us so that we can just graph them. So there's actually no procedure, which gives you additional time to get this all done in class, which probably happened. Okay, so our variables are that we're obviously looking at the velocity of cars, and we're looking at the time it takes to reach those velocities. And we've often said that time is pretty much always a particular kind of variable whenever it's involved. Okay, especially since time always goes on which axis? The x-axis. And there's a certain kind of variable that always goes on the x-axis. So time might be that kind of variable. Is that a big enough hint without me outright saying it? Okay. All right. And then velocity is obviously something that we're watching, okay, that we're hoping is going to change as a result of time. And then controlled variables. It's hard to have controlled variables when you're not actually doing an experiment. So what we have to do is we kind of have to envision how an experiment that would be testing the acceleration of various cars would be done. Okay, what kind of things do you suppose you would want to keep the same if you were testing acceleration for, you probably, for several cars, but probably each car gets run a few times. What kind of things would you want to make sure is the same between every run? Yeah, the track, right? Like we would want to make sure they're all on the same track. We don't want one of them going up a steep hill and one going down a steep hill and one on a level surface. It's hardly a fair comparison. Okay, so certainly the track would have to be something that we would want to keep the same. What else? Absolutely, the same driver would be a key. All right, you never know. I mean, someone who's an experienced drag racer would certainly do a much better job of launching a vehicle and accelerating it than you or I would do, who just gleefully mash the pedal to the floor. Okay, so yeah, things like that. What else? What else would be something we'd want to control? We said same track. We said same driver. Anything else? Okay, to an extent, yes, but we are looking at many different cars. We're not actually comparing the cars per se in the experiment. We're just comparing velocities and time. So we are going to have different cars, so that won't be a controlled one. But is there anything else that might affect how well a car accelerates? Okay, maybe. Okay, same fuel. Again, that's going to depend on the vehicle. Some vehicles run on regular unleaded, and some require premium, and some require diesel. So we can't really make fuel controlled variable either. Okay, and that would be something that I would think would be a controlled variable, except that many cars are actually designed around a specific tire. Okay, which is why all sports cars and all vehicles in general do not have this. I wouldn't want to go and put the tires from my truck on a Lamborghini. They would probably rub on the inside of the wheel well, I would imagine. Okay, probably wouldn't turn them very well. Okay, I'm thinking of a very simple thing that would affect how well a car accelerates that we haven't listed here yet. If we look outside, we might think about it. Yeah, the weather. Okay, we probably want to race them all on the same day so that at least temperature is somewhat the same, because temperature makes a big difference. Okay, on how well, how soft the rubber on the tires is and all that kind of stuff. Okay, how well fuel combusts is also a matter of temperature. Okay, So those I would think would be our big controlled. So those ones we kind of generate ourselves or together here, just because we're not actually running the experiment. Okay, our hypothesis. Okay, so our hypothesis needs to be an if, and then statement that's not actually going to sound the way I have it written here. Okay, the if part should probably tell me what acceleration is. Okay. Okay, so if acceleration is, and you tell me what acceleration is, okay, and, well, we're not actually running the experiment, but the experiment would be that cars are accelerated to 100 miles an hour, okay? Well, actually, I don't have it in, I changed all of the stuff to meters per second. So it's actually all cars are run to 45 meters per second, okay? Then how am I going to calculate their acceleration? Okay, so the then part should be how something about how acceleration can be calculated from the graph. Okay, that's the kind of stuff we want to have in our hypothesis. Okay, so like I said, we're not actually performing this experiment because it would be, wow, it's too bad we're not, because yeah, I could deal with running all of those cars down the track. Absolutely bagging the crap out of them for a whole day. Okay, but I'm not that lucky. All right, so from the data sheet, you're going to select 5 cars to create a graph of velocity versus time. Okay, so you've got your list. I don't know if it's on your template or not, but it's in the lab handout file that I included. Okay, so you're going to pick 5 cars from this list, whichever 5 you want to do, right? And you are going to create a graph that has all 5 cars on it, just like we did with the carts in the last one. Okay, and we're going to plot the points on there with Google Sheets. Okay, and then not using rise over run, I forgot to change that. That should say y equals mx plus b. Okay. Would be the change in velocity divided by change in time, get the acceleration of each vehicle, okay? And for every graph, the initial velocity is probably going to be 0. Is that going to be necessarily true if Google Sheets plots it for us? Okay, so let's make sure that we change that, okay? Okay, we're going to say the initial velocity is equal to b. Okay, our initial velocity is b in this case, the y-intercept. Is that going to be very close to 0 for most cars? Ideally, yes, but actually we'll probably find that Google Sheets is not going to make it all as close to 0 as we would think, simply because of the way cars accelerate. Cars, remember we said, are not a good example of uniform acceleration because they have gears, and typically their acceleration tends to flatten a little bit in the higher gears. So when Google Sheets does a best fit line of this, it might draw it more like that, which means our y-intercept will not be 0. That's okay. We still want to have the slope of that line. Okay? Everyone all right with that? Okay. All right. Okay, so we're picking 2 points that we wish on the line. Remember that one of those points is the y-intercept, is b. Okay, so one of those 2 points is going to be b because we're going to be using y equals mx plus b for our slope calculations here. All right, so one of those points is going to be the y-intercept. So if we're looking at this, okay, and Google Sheets spits out our y equals, I have no idea what the slopes are going to be. Let's just say like 9.5x plus 1.2. Okay, well, one of my points is 1.2, and the x value at this is 0. X is always 0 at the y-intercept, right? That's why we use it. Okay. All right, so in the analysis, you'll have this little chart to fill in, okay? So you'll have the name of the cars that you're doing, okay? You'll calculate your slope and put the units in there, okay? You'll have B with units, which of course you just get from the equation, all right? And then rank it fastest to slowest. So 1 is your fastest, 5 is your slowest. And then the last thing that you've got to fill in as part of your analysis is what will the displacement of the vehicle be in reaching 45 meters per second. All right, so again, looking at y equals mx plus b, okay, that's going to require you to do a manipulation of that in order to find out what the displacement will be. Okay, everyone follow me there? All right. So question number 1 is fill that in, and you fill that in by doing questions 2 and 3. Okay, so questions 2 and 3 essentially fill in the rest of this chart here. Okay. Okay, and I do want to see for number 3 your work. Okay, so I want to see the equation manipulated and the numbers plugged in with the answers in units. Okay, so show me your work for that. You don't have to show me anything for number 2 because obviously Google Sheets is going to spit that out for us. Okay, then for your conclusion, you restate your hypothesis, tell me whether you were able to do what you said you were going to do, and there's no evaluation on this one. How come? Because we didn't do the experiment. Okay, so there aren't any sources of error. We don't exactly know how the data we acquired was arrived at, so we don't have any sources of error. So it saves you a little bit of time there too. Okay, now in order to do this, okay, when you open up in Google Classroom and you have this screen right here, all you have is the Google Doc for the lab report. You don't have a spreadsheet yet. Okay, I didn't include one this time, so you have to create one. So you click create and you click on sheets and it'll open up a fresh sheet for you, hopefully. Okay, there it is, and it titles it Need for Speed Lab with your name on it. Okay, and you can put in your data there. What should the first column be? Anybody know? Okay, I'm going to demo how this works here then. Okay, so what we have to do, unfortunately, okay, is we need to set this up so that, I'm just going to delete this sheet here. No, I can't. Okay. Just going to delete what I put in here. Actually, no, I'm going to do this. And cut that. I'm going to delete this. Okay, so here's what we're going to have to do. Okay, we're going to build one graph for each car, which isn't a really big deal because you'll actually be able to copy this column to every sheet that you do. So you won't have to type it in again. You're just going to have to type in the times for each car because we want time to be which variable? We want it to go on the x-axis, okay? Which means it has to go first. Google Sheets just defaults to that the manipulated variable is first, okay? Even though the experiment wasn't run that way, okay? The experiment was actually run that they timed it to a certain velocity, which actually made velocity the manipulated, but we don't want to do it that way, okay? We want to have it so that time is the manipulated. So I'm going to do the first one for the Ferrari, okay? And I just highlight it all, same as we did before, okay? I insert my chart. Okay, and I pick scatter plots, okay, same as we did before, right? And you can see here now that I've got speed on the y-axis, I've got time on the x-axis here, okay? I've got that kind of flattening curve, right? And we do all the same stuff we did before, okay, where we can put in our titles, okay? We can go to the horizontal and we'll say that that's, you know, time in seconds, okay, and I put in all those extra grid lines, not that it really matters. Okay, and then I go back up and I do the same thing for the vertical. Okay, it's going to be speed in meters per second. Okay, and it'll actually be better off this way because our graph won't get really crowded having 5 cars on it. Okay, so now I've got my graph built there. Then I can go down to here and I can put in a label for this here, for that series. And I want to put in the trend line. Okay, what kind of trend line do I want? Linear. I definitely want a linear line. So there it goes. It draws it for me. And then remember that we want to put in the label to be the equation. Right? So it spits it out for me there. All right? So that's what I do for the first one, and then I can insert that. Okay, I can move it around, same as we always do. Okay, we'll put that into our lab report. Then I'm going to put in another sheet, and the next sheet will be for my next car. All right, so I'm going to go back to sheet 1, and I'm going to bring this column over with me because I know I want it. Okay, and then I'm going to enter the data for the next car here and do exactly the same thing. All right, so I'm going to have 5 separate graphs. That's okay. Okay, it'll actually be a lot easier to read them, and they'll be a lot clearer that way anyway. All right, so you're going to be inserting 5 separate graphs. It doesn't end up being any more work because you'd have had to enter all those other columns anyway. All right, questions on how that one's going to work? Daniel? With the way they ran the experiment, yes, we don't want it to be that way. Okay, we're setting it up so that time was the manipulated variable, because otherwise our graph will be reversed and we're not going to get the units we want. Yeah, so we're doing good science in that we're making the experiment do what we want. Yeah, that's sort of good, pseudo good science. Yeah. Into the lab report, please. Yeah. Okay, any other questions there, guys? All right, keep her going then.